Welcome back to the deep dive. So today we're going to really shrink things down. We're looking at athletic performance, but right down at the molecular level.
We are. We're getting into the science of gaseous exchange, which
Hmm.
sounds complicated, but it's fundamental to the Cambridge AS level syllabus for sport and physical education.
Right. And our mission here is to really get under the hood. It's not just about, you breathe in, muscles work. We want to understand the engine, the actual physical forces at play.
Exactly. We're talking about the invisible mechanics that move every single molecule of oxygen and carbon dioxide around your body when you're moving.
Because if you think about it, whether you're a sprinter or a marathon runner, it all comes down to fuel delivery. You need to get the good stuff oxygen in and the bad stuff waste out. So what's the secret? What actually makes the gas go where it needs to go?
It's pure physics, really. The entire system is driven by something called partial pressures. And these pressures create what we call diffusion gradients. Essentially, gaseous exchange is just the movement of oxygen and CO2, and it's all based on a simple rule. Gas always moves from an area of high pressure to an area of low pressure.
So if you're a student trying to picture this, you should almost stop thinking about the body actively pulling air in. It's more that the gases are being pushed around by these pressure differences.
That's the perfect way to think about it. The body is a master at creating and manipulating these pressure imbalances to get exactly what it needs. That's the key insight. We're going to follow that pressure gradient all the way from the air you breathe down to the individual muscle cell.
All right, so let's start that journey where it all begins, the intake. We're in the lungs. This is the first critical point of exchange, right? Alveolar exchange.
Yep, the first stop. This is where the outside world, the atmosphere, meets your internal circulatory system.
And the action all happens at a very specific spot.
It does. It happens across this incredibly delicate boundary between the walls of the alveoli, those are the tiny little air sacs in your lungs, and the blood capillaries wrapped around them.
And that boundary is paper thin, I assume, for a reason.
Oh, incredibly thin. We're talking about half a micron. It's designed for maximum efficiency because that exchange has to happen fast.
Especially when you're gasping for air mid-race. So the air you've just inhaled is sitting in the alveoli, and it's full of oxygen. That means that has a high partial pressure of oxygen.
Correct. We call it a high PO2. It's sitting at about 104 millimeters of mercury. Now, compare that to the blood that's just arrived at the lungs.
That's the deoxygenated blood coming back from the muscles.
Exactly. It's dropped off all its oxygen, so its PO2 is way down, maybe around 40. And that difference, 104 versus 40, that's your steep diffusion gradient.
And that gradient is the force. It literally shoves oxygen molecules across that thin membrane from the lungs into the blood.
It's an instant rush. And at the very same moment, the waste is rushing out. That same blood is full of carbon dioxide, so it has a high PCO2, about 46.
Whereas the air in your lungs has a much lower concentration.
About 40. So CO2 flows down its own gradient out of the blood and into the alveoli, ready for you to breathe it out. It's like a perfect, instantaneous swap.
An amazing system. But once the oxygen gets into the blood, it can't just be floating around freely, can it? We wouldn't be able to carry enough.
Not nearly enough. It
Yeah.
needs a dedicated transport vehicle. And that's where hemoglobin comes in.
The protein in our red blood cells.
That's the one. It's the ultimate efficiency tool. As soon as oxygen crosses into the capillary, hemoglobin grabs onto it, binds with it instantly.
And why is that binding action so important for the whole system?
Well, think about it. If the oxygen just stayed free in the blood, the partial pressure of oxygen in that capillary would shoot up almost immediately.
And that would destroy the gradient.
It would kill the gradient. The whole process would stop. By binding the oxygen, hemoglobin effectively hides it from a pressure perspective. It keeps the PO2 in the blood low, which means the steep gradient from the lungs is maintained and oxygen just keeps flooding in.
It's like keeping the loading bay clear so the trucks can keep coming.
A perfect analogy.
Okay, so that's the first half of the relay race done. The fuel is in the blood, but now we have to get it to where the work is happening. So let's shift focus from the lungs to the delivery site, the working muscle fibers.
Right, and this is where it gets even more interesting because this part of the system is so dynamic, it has to respond to demand. So you have this blood arriving at the muscle, packed with oxygen-rich hemoglobin. The challenge now is getting the oxygen to let go.
To jump off the delivery truck. And for that to happen, the muscle itself has to create an even more attractive environment, a steeper pressure drop.
And it does that naturally, just by doing its job. Muscles are constantly consuming oxygen to create energy, to create ATP. So the partial pressure of oxygen inside the muscle cell is always lower than it is in the blood that's arriving.
So even at rest, there's a gradient.
Even at rest, the PO2 in the blood might be 95,
Yeah.
but in the muscle tissue it could be, say, 40. That difference is the delivery gradient. It basically sucks the oxygen out of the blood and into the cell.
Like an internal siphon. The harder the muscle works, the more fuel it burns, and the stronger it pulls that oxygen in.
Precisely. And once the oxygen detaches from hemoglobin and crosses into the muscle fiber, it doesn't just wander around hoping to find the mitochondria. There's another player involved.
A local receiver?
Local receiver, yeah. This is myoglobin.
Okay, so myoglobin works with hemoglobin, but it's specifically inside the muscle.
Yes. Think of hemoglobin as the long-haul truck and myoglobin as the forklift in the warehouse. Its job is to grab the oxygen from hemoglobin and get it to the production line, the mitochondria, as quickly as possible.
And how does it do that? Why does the oxygen prefer myoglobin?
Because myoglobin has a much higher affinity for oxygen than hemoglobin does, especially at the low oxygen pressures you find inside a working muscle.
Ah, so it's a chemical thing. Under those specific conditions in the muscle, myoglobin is just stickier. It effectively steals the oxygen away from the hemoglobin.
It pulls it right off. That's what makes the handoff so quick and efficient. And myoglobin also holds a small strategic reserve of oxygen, which is vital right at the start of exercise before your breathing has had a chance to ramp up fully.
That makes sense. Now, we've talked a lot about getting oxygen in, but you mentioned the CO2 imperative. Getting waste out is just as important for performance.
It's absolutely critical. If CO2 builds up, your performance will fall off a cliff.
Why is that?
Because CO2 is acidic. When it builds up in the muscle, it mixes with water and forms carbonic acid. This drops the pH, and the enzymes that make your muscles contract just can't function properly in that acidic environment.
So the working muscle, which is producing loads of CO2, creates its own high-pressure gradient for CO2 compared to the blood arriving.
A very high pressure gradient, yeah. And that pressure difference forces the CO2 out of the muscle and into the blood to be carried away.
Yeah.
If that doesn't happen efficiently, you fatigue. Simple as that. The CO2 gradient is just as important as the oxygen one.
What's so amazing is that this whole system isn't static. It adapts. The gradients at rest are completely different from the gradients during an all-out sprint.
And understanding that dynamic change is where real coaching insight comes from. When you ask an athlete to go from a jog to a sprint or to push through that last length of the pool, you are demanding a profound physiological shift.
So let's talk about that. How does high-intensity exercise make that diffusion gradient even steeper? It's not just that the muscle is using more oxygen, is it?
No, it's cleverer than that. The whole local environment changes to help out. When a muscle works that hard, two things happen immediately. Its temperature goes up and its pH goes down. It gets more acidic.
From the CO2 and other byproducts like lactic acid.
Exactly. And those two changes, more heat and more acid, act like a switch.
A switch for what?
They change the behavior of hemoglobin. They decrease its affinity for oxygen.
So the delivery truck gets less sticky.
Far less sticky.
Yeah.
The hemoglobin becomes much more willing to release its oxygen cargo right where it's needed most. It's a beautiful piece of biological engineering.
So you have two things happening at once. The muscle is burning O2 like crazy, which drops the internal PO2 and steepens the gradient already. But at the same time, the byproducts of that hard work, the heat and acid, are making the hemoglobin even better at releasing the oxygen.
It's a double whammy.
Ah.
It creates the most powerful pulling effect possible. The PO2 inside that muscle cell might plummet from 40 all the way down to 10, maybe even 5. That creates a massive, hyper-steep gradient.
Yeah.
And because the hemoglobin is already primed to let go, the oxygen just pours into the cells.
And that's what allows an athlete to sustain that peak performance.
That's it. That is what pushing the limits looks like on a molecular level.
So when we talk about things like high-intensity interval training, we're not just building muscle. We're training the body to get better and more efficient at creating and managing these extreme pressure gradients.
Absolutely. A good coach understands that they're manipulating these internal pressure systems. They're conditioning the body to handle those shifts in temperature and acidity, to optimize that microscopic exchange. At the end of the day, every tactic, every strategy relies on the body's ability to manage pressure.
So to bring it all together for you, the student, what's the big takeaway? We've seen that everything in performance really rests on managing these pressure gradients.
Yeah, we've covered the role of partial pressure as the engine, the hemoglobin-myoglobin relay system for delivery, and I think most importantly, how the diffusion gradient isn't fixed. It adapts and intensifies under the stress of exercise. That adaptability is athleticism.
So for a final thought to leave you with, think about the difference between an elite marathon runner and a world-class weightlifter. The runner needs a stable, efficient, moderate gradient for hours. The lifter needs a massive, incredibly steep gradient, but only for a few seconds.
The next time you're watching any sport, think about that. Think about how knowledge of these internal pressure systems, where every molecule is flowing down a gradient, is the key to understanding the external performance you see on the screen. It's the deep science behind the skill.
Understanding the pressure of performance is your key to a success. For more technical deep dives, check out reviseddirect.com.